So our next topic is functions, and we're going to spend some time on this because it's very important. You know what functions are, of course, from your previous courses. So after an introduction about generally why we want to use functions, if there are advantages and disadvantages, we're going to take a look at, we're going to look under the hood and see what happens when you define a function in your program. What happens when you compile it? What does the compiler do with your function? How does it set it up for what happens when you run the program? What happens at runtime? So we're going to look at what happens, what the compiler does with your function, and what's going to happen when the program runs. So let's start with the first question. Why use a function at all? What are the advantages and disadvantages of using functions? So let's take a look at a simple example, one that we've seen many times before. Say I want to swap two numbers, right? So let's say I do something like this. I say I have an integer t, and I have an integer I, which is, say, set to 10, and then an integer j, which is set to 20. Okay, so the situation looks like this. Here is I, that has a 10 in it. Here is j, which has a 20 in it. And let's say here is t, and t starts out with nothing in it, right? So how do I swap through here? Right, so you've seen this many, many times. You know how to do this, right? Basically, you say, well, in t, I want to put I, right? That's the first step. So the first step goes like this. This is step number one, and t will end up with a 10. And then what happens? Well, once you've saved the value of I in t, then you can go ahead and bring the j up into the I. So then you say I gets the value of j, right? That's the second step. So this 10 is now going to become a 20, right? So now there's going to be a 20 over here. And then so that's step number two. And then step number three is you bring the 10 back down over here. So step number three says take j, and into j, what you want to do is you want to put the value of t, right? So that's going to swap. So this now 20 is going to become a 10, and you've swapped those two variables, right? Now, you've seen this, of course, before. So now imagine you have a program, and many times in this program, you need to do this. You have two variables, and you want to swap those two variables. So, of course, what you could do is each time you could just take and you can write these three statements. It's not difficult. It's only three statements, and generally you'd recognize what those things do. The other possibility, though, is to simply define a function, say, called swap, right? And if for any two variables, I and j, if I want to swap I and j, I could just call the function swap. Now, if you think about it, which would you rather do? Well, clearly, the advantage is by defining the function swap, because, first of all, you type less each time, right? You have to type the three statements. You can just type this one statement. Not only that, the program becomes shorter, which is an advantage. And also, it's pretty clear what you do when you see those three statements. After a while, of course, you're recognizing you're swapping those values. But if you call the function, if you name it correctly, and you call it swap, whoever's reading your program, or when you come back later on and you look at your program, it's much clearer what's going on, right? Because you chose the name of the function that it says what it's doing. So it's easier to read and understand the program. Not only that, it lets you think on a much higher level. And that's the main advantage, right? So now you're thinking functionally in the sense that I want my program to first do this function and then do that function and so on. So instead of having a bunch of statements, by having these function calls, it's clearer to write the program, assuming you're implementing the functions correctly, and it's easy to read it, to reason about the program, and whoever sees it, they can maintain it much easier. So basically, you're going to be writing on a higher level, which will simplify things, and that's always an advantage, right? So those are the advantages of using functions, right? First of all, you write less. Number two, the program becomes smaller. It becomes easier to read and understand. And finally, the most important thing is that it allows you, by judiciously choosing the functions that you write, it allows you to think about the program in a much higher level, and in this case, higher level is simpler. Right? So that's what's gained. That's the basic thing that's gained over here. Are there any drawbacks when you use functions? And the answer is yes, and we'll be able to see them much more clearly as we go on with the next topic, as we go along in here. But the drawback basically is that when functions are called, instead of executing the program line by line, the call sequence it basically has to stop. Various things have to happen in the runtime stack, and then the computer passes control of the program to your function. It does various things, has to return. Other things have to happen in the runtime stack. So there is a runtime cost when you run when you use function calls, right? Is it a good idea? Is it a bad idea? It all depends on what the functions are. But there's a way of fixing that up, and that's called inlining. Right? What is inlining going to be doing? Inlining is going to allow you, when you write the program, you're going to write the function. In other words, we saw in terms of the swap, instead of writing those 3 lines, you're going to simply write swap, I and j. But then what will happen is when you say, if I would define the function swap and say inline, I would do it like this. I would say inline, and then the function swap is void. And I would say, then I say the name of the function. And I would say int I and int j, right? Just like that. And what inline does, it says that the compiler, when it actually compiles the code, what it's going to do is it's going to substitute what we saw before. In other words, it's going to take those 3 lines, and whenever in the source code, the function call is encountered, the compiler instead will write those 3 lines that we saw before, right? So you get essentially the best, it would seem, the best of both worlds. When you write the program, you'll of course have to have defined the function swap, but when you write the program, you can then use swap. When you read it, you'll see what it's supposed to be doing. Someone else is working on your code, they can also see what you're doing, but when the program runs, you're not going to incur the runtime cost, which we will see in a little while. Instead, the original code for the swap is going to be substituted every time the call is there. So you made this trade-off. In the runtime, you won't incur the cost, and you get to be able to write the program at a higher level. So that is inline. There are advantages and disadvantages of inline. So for example, let's take a look at this. What are the advantages of inline? What are the pros of using inline? Well, first of all, it's going to speed up the program because it's not going to call the function, right? What's happened is the compiler has substituted the body of the function instead of the call. It's going to save the overhead of the push and pop on the stack. We'll see what this means in a little while. It's going to save the overhead from returning. So basically, when you call a function, as we said before, it's going to stop the basic execution of the program. It's going to jump someplace else, do various things on the runtime stack, and then it's going to have to come back, right? If you use inline, nothing like that will happen because it won't be calling the function. It's going to just be executing the body of the function. Number 4, it increases locality of reference. What that means is that the compiler will be able to generate code that's going to run faster. We'll see later on what that means. And so these are real advantages. We won't see this right now because we don't have the basis to talk about it. But what is any of the drawbacks of using inline? Well, first of all, your program, the actual executable code, right? The program after it's compiled is going to be bigger, right? Because instead of having just a function call, which is, imagine like a go-to to a copy of where the code is once, right? When you have a function call, so the code is only kept one time. And every time you encounter in the program, the function call, imagine it's just going to do a go-to and then back to where it came from. So the actual code is appearing only one time, but once you say inline, it's going to take the body of it and put it every place that you had a function call. So it's going to increase the size. It means, second, of course, is that it's going to, at compile time, what's going to happen is instead of having the call, the code is going to actually be in the program, which means that if you change the code, now let's say decide I'm going to change how the function is implemented. If you didn't inline it, then it's going to simply be a call, and then the change program will be called and so on. All that will have to happen is you'll have to just recompile just that function definition. The rest of the program doesn't have to change, right? Because there's still a call in that same function, assuming that you have the same parameters and so on. It's just going to call it. Won't be a problem. But if you've inlined it, then of course you have to recompile the main program as well, because the main program is going to have to change because all the code from the body has to be there. So those are some disadvantages. So, and we'll see this more as we go along. So now we know what some advantages are, what some disadvantages are, and we know what inline is. So let's take a look at the first thing here. What happens when functions are called? We're going to look at recursive functions to do this. And before we understand what happens when the function is called, we're going to step back and see what happens when you define a function, right? We're going to use recursive functions. You've seen them in the previous courses because they let us, it's the same thing will happen in non-recursive functions, but it gives us a better way of explaining things, as you see, as we will go on. Okay, so first let's review what we mean by a recursive function. So what's a recursive function? A recursive function is a function that's defined in terms of itself, right? Of course, the question becomes, why is such a function not circular? The definition of such a function not circular. So we'll see in an example in a second, but a circular, what's an example of a circular definition? So I can define a circular definition as a definition of something that's defined in terms of itself. Right? In other words, a circular definition is a definition that is circular. So that's clearly a circular definition. But the way, if we write recursive functions correctly, they aren't going to be circular. So for example, let's take a look at, we want to describe a function that will tell someone how to walk 10 steps. How would you do that? Walk 10 steps. So you could do it something like this. So let's take a look at a function that's going to tell someone how to walk, let's say, n steps. Let's say 5 steps. So here's a road, and there are 5 steps. 1, 2, 3, 4, 5. So you know that every journey, the longest journey starts with 1 step. So you say, well, just walk 1 step, and then you can walk the rest. Okay, so if we wanted to write a function, say how far, let's say walk, so we could do it like this. So how would I write the function walk? So let's say I want to walk, let's say, n steps, right? So the first thing I would make sure of is there any steps left to walk. So if n is equal to 0, then you simply stop, right? There's no more walking to do. But if n is not equal to 0, notice you haven't walked any steps yet, so what do you do now? So then just take 1 step. And then just call the function walk again. But you want to do n minus 1 steps this time, right? So that would work, right? So why is it not circular? Because what's happening is part of the definition of walk is how many steps. So if you want to tell someone how to walk n steps, then you tell them take 1 step, but then you're going to call the function walk with n minus 1 steps. That's it's a different task than the walking of n steps, right? So it's not a circular definition. All right, so let's look at a very common first example, which I'm sure you saw in the earlier course, and that is to calculate n factorial. So we all know what factorial is, and factorial is the product of all the numbers from 1 to n. So, or you can go from n down to 1. And so this allows us to see the essential recursiveness of this process, because let's say 5 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. But if I look at this, this is really 4 factorial. So I see that 5 factorial is really 5 times 4 factorial, or in general, n factorial can be thought of as n times n minus 1 factorial. Um, and so the main thing, of course, we have to make sure we don't go into infinite regress. So if I want to, in other words, I have to have a place to stop. So if I want to write a recursive function to do this, that turns out to be pretty trivial. So let's say fact is the function we want to write. So I want to write a function called fact of n. So what is n going to be? N is going to be an integer. So I have an integer n is my formal parameter here, and factorial is going to return an integer. So how do I do this? Well, it's basically this definition, but I have to make sure that I'm doing something. So if n is going to be equal to 1, don't worry about 0, forget about 0, but if n is equal to 1, then I simply want to return 1, right? That's the base case, return 1, right? That's called the base case. That's where we stop, and there's going to be no additional calls on the function. But if n is not equal to 1, so I simply want to return what? What is going to be, if n is not equal to 1, I want to return whatever the current value is n is, and I want n times calling the function factorial on n minus 1. And that's the whole story, right? That's the whole business. And it's just like what we said before, if you want to walk n steps, you first walk one step, and then you call, then you can walk n minus 1 steps, right? So this is the definition of factorial. And the base case in this case is n equal to 1. And the base case is needed because we want to be able to stop this thing, right? If we wouldn't have a base case, we would go infinitely down. We'd have an infinite regress. So, for example, let's say if you wanted to compute 3 factorial with this function, right? So we're going to call factorial of 3. Let's say f is factorial. So what the function says is it the case that n is equal to 0. There's going to be n. The answer is no. So that's going to be, equal to 1. Forget the base case, though. We had no base case. So that's going to be, well, what is that going to give us? That's going to give us 3 times factorial of 2. But this, we still have to call factorial. So that's going to be 2 times factorial of 1. And if you have no base case here, that's going to be 1 times factorial of 0. And that's going to be 0 times factorial of minus 1. It's going to keep going down and down. So we need some place to stop, and that's the base case. Here the base case is 1. So what will happen in this case is that when we call factorial of 1, the function will simply say 1, and we're going to then wind our way back, right? And we'll be able to calculate it. That's the way this thing works, right? So if we do it that way, 3 times factorial of 2, it's going to be 3 times factorial of 2 times 1. So it's going to give it, it's going to go all the way down here, and we're going to end up with a 1 and then a 2, and it's going to give us 3 times 2 times 1, and that's going to be a 6. Okay, so the base case is important. Does it make a difference where we put the base case, right? Where we place it? Of course it does, right? If you look over here in the function, if I put the base case instead, if I asked it at the bottom, right? If I took this question over here, is it equal to n equal to 1, and I put it after, say, the return, that's not going to work, of course, because every time we're going to come back and again, we're going to call factorial without even checking to see that we need to stop. So that is not a good idea. And the idea is that when you come into the recursive function, the first thing you need to do is check if the base case holds. If it does, then do whatever needs to be done with that case. Otherwise, you go on to the recursive part. So that's I'm sure this is nothing new. Okay. What's going to happen? Here's where it gets interesting. What's going to happen when the function gets called? What's going to get function when it gets called? So let's actually trace it and see. Let's trace this thing and see. Say you have a number of different functions, right? Let's say you have a function f, and the function f calls, let's say, some other function g. And that function calls another function h, and that function calls another function, let's say, k. Well, clearly the computer has to have all the code for f, and then all the code for g, and all the code for h, and all the code for k. And then k will do the computing, and then it's going to come back and return a value possibly, or just return the control of the computer back to h. And then when h finishes, it's going to go here and then when that finishes, it's going to go back to F, right? So, but if these are all different functions, of course, the computer has to have internally, it has to have the code for each one. So let's say instead of F calling G, these are all different functions. What happens if F calls F? In other words, let's say F stands for factorial, and I want to compute factorial of 3. So as we saw before, to compute factorial of 3, there'll be a call on factorial of 2. And then to calculate factorial of 2, there's going to be a call on factorial of 1. So the question is like this: do I actually need 3 copies of the code? When F called G, called H, called K, I needed, of course, the copy of the code for each one, but do I need to have it here as well, right? Do I need one copy of the code for processing the F of 3 and another one for processing F of 2 and F of 1, or can we somehow get away with that? So the answer is you do not need multiple copies of the code. You can, in fact, get along with just one. And how would that be? So think of the following analogy. Imagine that there are 350 students in a class, and we're all taking a midterm, and we distribute 350 blue books. So now the question is, do I actually need 350 copies of the exam or not? So let's say it's a short exam. And could I do the following? Could I project on the screen in front of the class, could I just project the 3 questions? And then all the people in the class, they can work on the problems in their own blue book, and they can all reference the same questions, right? So in fact, even though there are many, many people taking the exam, as long as we have individual copies of places to do the work, to store the partial results, I don't really need multiple copies of the questions, right? So the same situation actually holds when I'm doing these calculations in recursion. I can have one copy of the program as long as every time I call it, I have an individual place to store the information. And that's called an activation record. And sometimes it's also called a stack frame, and it's going to be stored on the activation stack. So what does that mean? What's the idea of a stack? So this is a very important data structure, and when you take the data structures course, you'll learn about it extensively and so on. Perhaps later on in the semester we'll actually write one like this. But basically the idea is pretty straightforward. What's a stack? What's a stack? So here's a common analogy that's used. It would seem very strange, I think, to most of you. But when I first started teaching here, when you went into the cafeteria, you didn't get styrofoam plates and bowls. You actually got a real plate. And there was in the back of the kitchen, there was someone who was washing the dishes. There was a big machine that was washing the dishes, and a person would come out and they take the dishes, and what they did was there was like sort of a little metal table, and as the dishes came out, this person, the dishwasher, would actually put the dishes, he would actually push the dishes into this contraption over here, and the contraption sort of had a spring in it. So what he did was he'd take the first dish and he would put that dish in here, and then the dish would sort of pop up because it was a spring in there, you saw the top of it. And so this is the first dish that he put in. Then he would come, and the second dish, he would put the second dish on top of that. So the second dish is now popped up to the top, and the third dish, and so on. So he would stack the dishes, right? He would stack the dishes. And what happened when he stacked the dishes was the last dish that came in, right? Let's say dish number 3, right? 0, 1, 2, 3, dish number 4. So the last dish that came in, if someone then took a dish and went to get their food, that was the first one that came out. Let's call LIFO, right? So the last dish, that's a stack. So the last dish that came in is the first which comes out. So there's 2 operations basically on here. When you put a dish on, that's called pushing the dish. And then when you take it, you pop the dish off the top of the stack, and then the stack sort of, pushes itself up, and then you get the next one, and so on and so forth. So that's what a stack is. And that's how pretty much when a recursive function is run, and in fact, as we'll see later on, any function that's being run, this thing happens internally in the RAM, specifically in the runtime stack, right? We called it a runtime stack. We didn't say why it was called a stack, and this is why it's called a stack, right? So here's the idea. What you need is an activation record or a stack frame for the function that's being called. What does that mean? What is an activation record? What does that mean? So here's the factorial function, right? This is what we looked at over here. And you can think of the activation record as sort of a template, a place to store all of the information necessary to run that function. It's like the blue book, right? So what will happen, it's going to look like this. Here's one way of looking at the activation record, right? So what's going to be in the activation record, a number of things. First of all the parameters are going to be in the activation record, right? So anytime I have a parameter, right, that's going to be here. So if you look at the function f, the factorial function, how many parameters do I have? Only one, right? So I'm going to have to keep track of n, right? In my blue book, I'm going to have to keep track. Now, any local variables are going to have to be kept in the activation record. Are there any local variables? Well, there aren't, not in this particular example, so no local variables. And then the return pointer. That's where do I go back to when I finished the function, right? So that's going to be a return address. Make sure understand what's going on over here. So let's say we don't have a recursive function, right? So I have f calling g, calling h, let's say calling k, right? So what happens is f is some code, right? In the middle of this code, it's going to call g. And g is going to have its own code. It's going to end up calling h. And then h has its own code, and it might call k. And here's k's code. Now, at some point, k is going to return. So when h calls k, if there's any parameters that have to be passed to the k, it's going to, of course, have to pass those parameters. But when it finishes, when it does the equivalent of a return, to where does it return, right? Where does it go back to? So somehow when h calls k, it has to pass to it, besides just the arguments that it needs to calculate with, it needs to pass it the information of when it finishes, where do I go back, right? The return address of where to go back. So then what will happen is this will go back over here, and the function h will continue on where it left off. So if it calls from here, after returns, it's going to come back over here. Likewise, when this guy says return, let's say at the very bottom, return to where, so h also has to have the address of where to return to g. So since it called over here, it's going to have to return over here. And so that's the idea. So when a function gets called internally, it has to pass whatever arguments it needs to pass, but it also, of course, has to pass the return address, or else you can't get this thing to work, right? That's pretty clear, I think. So let's see what happens in the case of a factorial. Let's say I do the following thing. I have my main program. So my main program is going to say something like C out the factorial of 3. And once it does this, of course, the main program is going to stop, right? And it's going to make a call on the factorial function. So the compiler sees that this is a function call. And so what it's going to do, the compiler, at the time that it gets compiled, it's going to look at the definition of the function, and it's going to create an activation record, right? As we saw, the activation record has two things. It has the variable that's being passed. It has, in this case, no local variables, and it has a place to return to. So let's look at the main program, right? Here's the main program. So when the function f returns with 3, where's it going to return to? It's going to return to this place, right? To this place, to the output, and print the value that's been returned, right? Let's call that point 1. So when this function is called, when f of 3 is called, there's the main program, of course, has its own code. So there's going to be a call on f. It's going to say this is going to call f of 3. So it has to somehow pass the address of the next machine language instruction to execute, right? This, of course, when it's running, this is not going to be a high-level language anymore. It's going to be machine code, the binary. So it'll pass the address in the binary where to come back to. So what'll happen is, if it calls f of 3, n will be equal to 3, and let's say the return, let's say the address is what we've called 1. Okay, so the first thing that happens when this function is called, f of 3 is called, is at runtime, before I even calculate anything, the compiler has already generated the code to take this activation record that it's constructed during compile time and to push it, right? To push it onto an internal stack, right? And that's called the activation stack, right? So it will push this as like it writes down these values, the n and the return pointer, and then it's ready to run. So before it runs, it's going to construct this activation record and push it onto the stack. So now it comes in here with a value of n equal to 3, right? So the value n now is equal to 3, and it's ready to go. So it comes in to this line over here, right? It comes to this line over here, and it's asking, is it true that n is equal to 1? So which n is it talking about? It's always talking about the n at the top of the stack, right? Just like with those dishes, could be 100 dishes in there. You have no idea. You don't see any of the ones except the one on the top. So likewise, this is a stack like that. Every time a call is made, a new activation record is going to be pushed onto this activation stack. And when the program, in this case factorial, refers to a variable, it's always referring to that value of the variable on the activation record that's at the top of the stack. So it looks in over here and it says, is n equal to 1? Of course, n is not equal to 1, it's equal to 3. So you don't do a return. What you're doing now is you're going to come down over here and you're going to try to return n times f of n minus 1, right? So you can't really return anything yet, because even though you know the value of n is 3, but you don't know the value of n minus 1. So there's another call on the function f. What happens when you make a call on the function f? Every time you make a call on a function, a new record is pushed onto the activation stack, right? And what you're trying to do now, you're trying to do f of 3. So it says in order to do f of 3, you need to do f of 2. So f of 3 is going to call f of 2. But before it can calculate f of 2, it has to put the record on the activation stack, and it has to populate it, right? So if the current value of n is 3, on the next on the new activation record on top of the activation stack, that's going to be a 2 now, right? It hasn't done any calculations. It's pushing the record onto the stack, and it's populating it, and then it'll go do the work. Now, what's going to happen? Where do you go back? When you come back, where you're going to go back? You're going to go back to this multiply, right? In other words, when this f of n minus 1 or this f of 2 finishes, and it's going to go back, it's going to go back to that multiply, right? So what should we call that multiply? What position? What should we call that? It's going to be some specific address. It's no longer the address that we called 1, because that's back in the main program. Let's call that position over here. We're going to call it 2, right? So 2 is going to be the address of the multiply that's going to be executed once this call finishes. Okay, does that make sense? Okay, so we have, hopefully, so now we're ready to execute the function again, and we come into the function and we say, what's the value of n at this time? The value of n is going to be 2, right? Because it only sees the top of the activation record. So it says, is n equal to 1? Well, of course not, because n is equal to 2, right? So it does not do the return, but what it does, it comes down to this over here, and it's going to do n, in this case, n is equal to 2, times something else, times some other call in the function. But since we don't know the value of f of n minus 1, it can't calculate it. It's got to make another call, right? So f of 2 is going to make another call on f of 1, right? So what happens when you make a call? We saw that a new record is pushed on top of the activation stack. You populate that, right? So if currently n is equal to 2, the new value of n is going to be equal to 1. And where are you going to come back to? Where are you going to come back to? So since you're making this call over here, you're going to come back to that same green thing. You come back to the multiply, and so that's going to be the same point too. So I want you to make sure you understand that how many copies of the code, right, the machine language version of the code, how many copies of this code? There's only one copy. So how does that work? Well, because every time you make a call, you're opening up a new blue book, right? You're opening up a new place to write the values, and you can always refer to the same set of instructions. But the difference is, whenever you say n, it's going to be a different n. So the instructions are going to stay the same, but the place where you record the values of the variables and the local variables and the parameters and the return pointer, that's going to change. But you don't need to have copies of the code as long as you have a place to keep the current value, the state of your calculation, separate from what you did before, right? All right, so that's a very cool idea. So let's see what happens now. So we populated, right? We're now doing this guy over here. So we set up the activation stack, the activation record. We push this on top, and we're going to now do the calculation again. And now, what's going to be the value? What's going to be the value? This is an n, right? What's going to be the value of n? The value of n is going to be 1, right? The value of n is going to be 1. So it's going to come here and say, is n equal to 1? The answer is yes. So this is, I'm sorry, I left out something over here. This should say return what? Return 1, right? It should say return 1. There's nothing there. It should say return 1. Okay, so we don't come down here and do this anymore. We're ready to return. We turn this value here. So what happens now is that what's going to happen when I say return? So return means you've got a value that has to be returned. What is the value? That's going to be 1. Now, where do you keep this value? That's an interesting question. That really depends on the particular compiler and how it's set up. We're going to imagine that what happens is there's some place that the compiler knows about. You go through all the various possible ways of implementing this. You'll take a programming languages course later on. But let's imagine there's some place that the system knows where the return value is going to be kept. It could be kept on the activation stack and accessible from the lower values, but imagine there's some place. So when it says return 1, 2 things are going to happen, right? Number one is the value will be placed in that place, right? Store the return value. So you're going to put the 1 over here so that it can actually be returned. And number 2, what you're going to do is you're going to pop the stack, right? Because right now we're doing this one, but we're going back here to pick up where we left off on f of 2, right? Imagine just a complicated calculations. Imagine that you're doing some calculation and it's very, very complicated. So you take a piece of paper, right, and you put on your desk and you're just calculating, and then you wrote all over the place here, and then it turns out that in the middle of this, you need to do another calculation. And also, so you get another piece of paper and you put that piece of paper on top and you do all your calculations here. But imagine you have to do another very complicated, see another piece of paper, you put that over here. And when you're finished, what are you going to do? Let's say this is the result of the calculation. So you take this result and you throw the paper away, right? And you come back to the place where you left off, and you're going to go back and finish these calculations. And then finally, when you finish these calculations, you're going to take it and you're going to go back to where you were originally, and you're going to be able to finish the calculation. So that's basically what happens over here, right? Every step of the way, instead of pieces of paper, we have these activation records. Okay, so you're going to pop the stack and return the value. That's the second thing that happens. So what that's going to look like is you're going to return a 1 for the calculation, and you're going to pop the stack. Now, what is this 2? Don't forget about this 2. That's where you're returning. That's where you're returning 2. So you're going to take the 2. You're going to go back to step 2. What is step 2? Step 2 is this green place. It's the multiply. So you're going to take the value that you're returning for f of n minus 1. You're going to take that value and multiply it by the current value of n. So you pop the stack. You can get rid of the top of the stack. This is no longer going to be here. But we remember we're going to go back to 2, and we're going to take the value of this call. Now we know what it is. The value is 1, and we're going to multiply 1 times n, right? We're going to multiply the 1 times n. But what is n? N is the number at the top of the stack now. What's on the top of the stack? It's 2, so it's going to be 1 times 2. And then what? And then you are going to return. So what does return mean? What does return mean? Well, return, we saw what it means, is takes the value that you just calculated, right? What's the value? It's 1 times 2, which is 2. Put that in that special place, right? Here's the special place, and return to where you were called from, right? So where were you called from? Remember, you have only one copy of the code. Again, you were called from this green thing over here. You go back to do the multiplication. So you store the value of 2, you pop the stack, but you can go back to step 2 in the previous level. So we get rid of this. We're going to pop the stack. We're back in step 2, and it says, okay, take the value that you just returned, which is the 2, which represents the 1 times 2, multiplied by the current value of n. What's the current value of n? It's 3, right? It's 3. And then what? And then return, right? Then return. What does return mean? Take the values calculated, which is 6, right? And put it in that special place and return. Now, return to where? Return to where? Well, this address tells you what to return to. To return to where means you're going to go back to point 1. What's point 1? Point 1 is the output in the main program, right? You're doing the cout in the main program. So you've just calculated the value. The value is going to be here, this 6. You come back over here and you resume, and you're going to print out 6. But before that, of course, you're going to pop the stack. And that is how this works. It's a little bit complicated. So I think if it's not absolutely clear, try to listen to it a number of times until it actually makes sense, right? But basically, what do we see here? What's the main point to take away? That when you have a recursive function, you don't need more than one copy of the code, right? You just need a place to store every time the function gets called. You need another place to store the relevant data. What's the relevant data? Relevant data is the current value, in this case, of the arguments. In this case, n is the only argument. Any local variables that you might have. In this case, there are no local variables. A place to store the return address. When I finish this level of the calculation, where do I go back, right, to pick up where I left off? Which, when I throw the top piece of paper away, I got to remember where I go back and continue the calculation on the papers below. And that's basically the story. So we have this example of what happens internally when you actually do the calculations. Now, just one final point: where is all this? Where is the runtime? Where is this activation stack stored? Right. The activation stack is every time I call an activation, I got to push it on the stack. So remember this diagram that we had the last time. So we have the data over here and so on. And then the various, I'm sorry, this is not the data, this is the functions were over here, right? This was these were the functions, right? And over here was the various data. So we had the runtime stack. So what happens to the runtime stack? Well, the individual variables, and then in the runtime stack is also the activation stack that we saw is going to be stored in this place over here, because this automatically happens, and so that's where it goes. Remember, down here there was the heap and so on. So the runtimes, the activation stack is going to be stored in the area that we have for the runtime stack. We're going to now look at another example of recursion, also a very famous function called Fibonacci, and we will see that right now.